All right, this is part 2 of the review for the Unit 2 test. This part of the review focuses on nuclear equations and half-life. So in these problems we're going to be balancing some equations, and we'll talk about the types of decay that are going on. So here we have bismuth 214, so the atomic number on the bottom 83, mass number on the top is 214, element 83 is bismuth. And as we look over here, we see that we have a particle with no mass and a -1 atomic number. That's beta decay because that's a beta particle. So in order to balance the equation, we need to make sure that the numbers for mass and atomic number are equal on both sides. So this is a 0, which means the total mass of the what's called the daughter atom is going to be the same, 214. The atomic number, in order for the total on the right-hand side to be the same as the total on the left-hand side, we need to add to the atomic number because we have a -1 here. So 84 plus -1 is 83. So the total on both sides is the same. Then we would need to look up element number 84. So if we look on the periodic table, element number 84 is polonium. So we write PO for polonium. So again, the key here is that the numbers for mass are the same total on both sides, and the numbers for atomic number, 84 and -1 equals 83. And since we changed the atomic number, we have a new element, polonium, which we figure out by looking it up on the periodic table from its atomic number. In this equation, we have thorium, 230. The mass number is 230. The atomic number of thorium is 90. On the right-hand side, we have this particle with a mass of 4 and an atomic number of 2. That is an alpha particle. So this is called alpha decay. We can also write that as 4,2He because the alpha particle is the same as a helium nucleus. So again, the key on balancing the equations is always the same. We want to make sure the total numbers on both sides add up. So 230 for thorium, this is 4. So that means the mass number for this daughter atom has to be 4 less. That's 226, not 236. Okay, so that the total is 230 on the right and 230 on the left. Since this is a 2, that means that this atomic number has to be 88. So 2 less than what we started with, because 88 plus 2 equals 90. Now the total on both sides is the same. We look up element number 88, that is radium. So again, because we changed that atomic number, we have to change the element. So the equation is now balanced. 226 plus 4 is 230. 88 plus 2 is 90. And again, since we changed the atomic number, we have a new element. It's no longer thorium. It is now radium. So that equation is done, and that's alpha decay because of the alpha particle. This equation is slightly different because we actually have an extra particle on the left-hand side of the equation rather than the right. But the process is going to be the same. We're going to make sure that the total numbers on both sides are equal, and if we change the atomic number, we have a new element. In terms of what type of decay this is, since this is a beta particle, which is the same as an electron, what's actually happening is we're adding an electron to this atom. That's called electron capture. So this type of decay is called electron capture. And then to finish the equation, again, we have the 0 here, so the total mass on both sides is 239. Since this is -1, 92 plus -1 is 91. So the mass on both sides is the same. 91 is the same as 92 plus -1. So now we have a new element. We have to look up element number 91, which is protactinium, and it has the abbreviation PA. So mass numbers are the same on both sides. atomic number is the same on both sides. We change the element to protactinium by looking it up on the periodic table. This problem is set up a little bit differently because we're actually going to identify the original atom, what's called the parent atom, by looking at what we have as products on the right. So this one's also different because it includes an extra item here. On the right-hand side, we have these, what are called gamma rays. Okay, the gamma rays have no mass and no atomic number, so they don't affect any of the calculations we're going to do. The gamma rays are essentially radiation energy that is released as a result of this reaction. So in order to identify the parent atom on the left, all we have to do is add up all the numbers on the right. So the mass of 4 plus 234 plus 0 is a mass number of 238. And then the atomic numbers on the bottom, we have 2 plus 92 plus 0. So the atomic number is 92. And then we look up number 92 on the periodic table. That element is uranium. Okay, so in this case, what we did is we worked backwards to predict what we started with. We started with uranium-238, which decayed, alpha decay, because of the alpha particle. And the daughter atom, in this case, was thorium-234. Atomic number 90, mass of 234, that's thorium, as we would see on the periodic table here. And then the gamma rays, again, they're part of the reaction, but they don't affect any of the numbers that we use in the calculations. So 234 plus 4 is 238, 90 plus 2 is 92. The equation is balanced. The element is different because the atomic number changed. All right, so we have iodine 131 on the left. We have this, which is the beta particle. So this is beta decay. And to identify the daughter atom, we take the mass, right? 131 on that side, which means this has to be 131, 131 plus 0. And since this is -1, the atomic number is 54, because 54 plus -1 is 53. The total on both sides is the same. And then we'd have to look up the new element. Element number 54 is xenon, symbol Xe. So the daughter atom is xenon 131, and the total 131 plus 0 is 131. 54 plus -1 is 53. We have the equation balanced. This is a similar equation. This is beta decay because of the beta particle. But similar to the problem a couple questions ago, we're actually predicting or calculating what the parent atom was rather than the daughter. We have the product here, so we have to work backwards to make sure that all the numbers add up on both sides. That doesn't change depending on which direction we're going. It's always the same idea. Make sure the total numbers on both sides for mass and atomic number are the same. So 14 here plus 0 means the parent atom had a mass of 14. 7 plus -1 means the parent atom had an atomic number of 6. Element number 6 on the periodic table is carbon. So we have carbon 14 undergoing beta decay to become nitrogen 14. Atomic number 6, -1 plus 7 is 6. Mass number 14, 0 plus 14 is 14. The equation is balanced. Okay, so working backwards again. This is the alpha particle, so alpha decay. The daughter atom here is polonium, PO, 84. It's polonium-210 is the name of it because it's polonium with a mass of 210. Since the mass of the alpha particle plus the mass of the polonium atom is equal to 214, that was the mass of the parent atom. And the atomic number 2 of the alpha particle and the atomic number 84 of the polonium gives us a parent atom atomic number of 86, so we can look that up. Number 86 is radon, symbol Rn. So radon-214 undergoes alpha decay to become polonium-210. 210 plus 4 is 214. 84 plus 2 is 86. Look up number 86, it's radon. That's the new element. Okay, we have protactinium undergoing alpha decay. Protactinium-234, the alpha particle has a mass of 4, so the resulting atom will have a mass of 230. Since the alpha particle has an atomic number of 2, and the parent atom, protactinium, has 91, the new atomic number is 89. 89 plus 2 is 91. 230 plus 4 is 234. All the numbers are the same on both sides of that arrow. Look up number 89. That is actinium, symbol AC. So we change the atomic number, we look up the new element, make sure all the numbers on both sides add up to the same thing. The equation is now balanced. Okay, so this is protactinium-234 again, the same parent atom we had in the last problem, except this time it's gaining a beta particle or an electron. So this is electron capture, would be the type of decay. But as with all of these, the process is the same for filling in the blank. 234 plus 0 is 234. 91 plus negative 1 is 90. Okay, so the totals are the same, 234 plus 4, 91 plus negative 1. Look up element number 90 on the periodic table. It's thorium. So the totals add up on both sides of the arrow. We changed the atomic number, so we had to look up the new element on the periodic table. It was thorium, number 90. The equation is balanced. Okay, last one. This is a little bit different. This is, instead of a beta particle, this is what's called a positron. So this would be called positron emission. We're giving up a positron. But, again, the process is the same no matter what type of decay it is. We're going to figure out how to make everything add up to the same thing on both sides of the arrow. When we change the atomic number, we'll look up the new element and fill that in. So the positron has no mass, so the mass number of 220 is the same on both sides. The positron has an atomic number of positive 1, so 86 is the same as 85 plus 1. So again, don't think it's 86 plus 1. It's everything on the left has to total the same thing as everything on the right. So 85 plus 1 is 86. And then again, since we changed the atomic number, we have to change the element. It's no longer radon. It's element number 85, which is astatine, symbol AT. Positron emission, different type of decay, but you do everything the same way. Total is 220 for mass on both sides. Total is 86, or 85 plus 1, which is 86 on both sides. The equation is now balanced. Now we're going to take a look at some problems involving half-life calculations. In order to solve these equations or these problems, the key thing to remember is that every time you go through a half-life, you eliminate half or divide your sample in half. So you start at 0 half-lives, so that's your starting point, 100 atoms. Okay? How much would remain after 1 half-life? Well, 1 half-life means divide your sample in half once. So 400 divided in half would be 200 atoms. Then after another half-life, so we go from 0 half-lives to 1 half-lives by dividing our sample in half. Each time you go through another half-life, you divide that second sample or the next sample in half. You don't take 400 in half and then take away the other half. That's not the way it works. you divide each remaining sample in half. So 200 after one half-life becomes 100 after two half-lives. After another half-life, we divide this in half. It becomes 50. And then after four half-lives, so we go from 0 to 1 to 2 to 3, and then four half-lives would be 25 atoms. So after each half-life, you divide whatever amount you had in half. And this would go on and on and on for however many half-lives there are. Okay, so similar type question. We start with 16 grams. The question is, how much would there be after three half-lives? So I always like to start out by remembering that we're starting with 0 half-lives. We haven't started the clock yet. So at 0 half-lives, we have, according to the question, 16 grams. So we have to get to 3 half-lives. So we're going to divide this in half 3 times. After 1 half-life, dividing that in half, we'd have 8 grams. After 2 half-lives, divide that in half, we'd have 4 grams. And then after the third half-life, which is what the question asked, divide that in half, we have 2 grams. So divide in half, divide in half, divide in half. 3 half-lives. Okay, so the final answer here is 2 grams would be left after the third half-life. Okay, slightly different question. We start with 100 grams, and it decays down to 12.5 grams. That takes 21.6 seconds, and the question is, what is the half-life? So we have to do a little bit more work in this case, but the concept is the same. The first thing we need to do is figure out how many half-lives is this. We know the total amount of time. We need to know how many half-lives that time represents. In order to do that, we have to figure out how many half-lives did it take to go from 100 to 12.5. So let's start, like we've been doing. At 0 half-lives, we have 100 grams. After 1 half-life, we would have 50 grams. After 2 half-lives, we would have 25 grams. And then after 3 half-lives, we would have 12.5 grams. And that's what the question gave us, 100 down to 12.5. In order to do that, I had to go 1, 2, 3 half-lives. Okay, so that's the first part of the information that we need. So 3 half-lives took 21.6 seconds. So 21.6 seconds equals 3 half-lives. So in order to figure out what 1 half-life is, I'm going to divide both sides by 3. So 1 half-life equals 7.2 seconds. 21.6 divided by 3 is 7.2. So 7.2 seconds would be 1 half-life. It took 3 half-lives to get down to 12.5. That's the 21.6 seconds. All right, so this question is similar to the last question, except instead of giving us the total, the question gives us 1 half-life. Okay, 1 half-life is equal to 3 minutes, a little over 3 minutes. So how long will it take to go from 120 grams to 7.5 grams? Again, just like in the last question, the first thing we need to know is, well, how many half-lives does that take? And then we can take the number of half-lives times the length of 1 half-life, and we'll get the total time. So 0 half-lives, we have 120 grams. We need to get to 7.5 grams. After 1 half-life, we would have 60 grams. After 2 half-lives, dividing that in half, we'd have 30 grams. 3 half-lives, divide that in half, gets us down to 15 grams. And then after 4 half-lives, dividing that in half, we would have 7.5 grams, which is what the question asked. How long does it take to get down to 7.5 grams? Well, it takes 4 half-lives to get there. Each half-life is 3 minutes long, 3.03. So 4 half-lives times 3.053 minutes per half-life, right? That's what 1 half-life is, gives us a total of 12.212 minutes. So the answer here is 12.212 minutes. Even though this is worded differently, this is the same exact type of question that we just did. We're given 8.1 days is equal to 1 half-life. And then we're asked to figure out how long would it take for a sample to decay from the starting amount to the ending amount. Same question, different numbers. They put in different elements and isotopes. But the key factors here are a half-life is 8.1 days, and we need to know how long it takes to go from 50 grams down to 6.25 grams. How many half-lives is that? At 0 half-lives, we have 50 grams. After 1 half-life, we would have 25 grams. After 2 half-lives, we'd be down to 12.5 grams. After 3 half-lives, we'd be at 6.25 grams. Okay, so that's what they asked us to find, 50 to decay to 6.25. It took 1, 2, 3 half-lives. Each half-life is 8.1 days. So 3 times 8.1 is 24.3 days. So the answer is 24.3 days to decay from 50 down to 6.25. This question is similar to the last couple, but asking it a slightly different way. Instead of giving us the starting and ending amounts, they give us half-life. They give us the total time. Instead of trying to figure out the total time, they're giving us the total time. And they're giving us the starting amount. Then they want us to figure out how much would be left after the amount of time gone by. So in the last problems, the last couple problems, we had to figure out the number of half-lives and then multiply that by the time of 1 half-life to get the total time. In this case, we're going to take the total time, divide it by the number of half-life, or the time of 1 half-life. That will tell us how many half-lives it is. And then we can do our half-life calculations to figure out the remaining amount. So if the total is 62 hours and 1 half-life is 12.4 hours, 62 divided by 12.4 is 5. So the time that they're giving us is equal to 5 half-lives. So now we need to figure out, if we start with 848 grams at 0 half-lives, how many would be left after 5 half-lives? 1 half-life. Dividing that in half, we'd have 424. After 2 half-lives, dividing that in half, we'd have 212. 3 half-lives, Dividing that in half, we're at 106. After 4 half-lives, we divide that in half, it comes to 53 grams. After 5 half-lives, dividing that in half, we would have 26.5 grams. 5 half-lives is the total amount of time we're talking about. After 5 half-lives, we would have 26.5 grams remaining. Okay, so remember, half-lives is all about dividing in half. Another type of question that I could ask would be this one backwards, giving you the 26.5 and asking how much did you start with if it gets down to 26.5 in 62 hours. If I asked you that, instead of dividing by 2 5 times, you'd multiply by 2 5 times. So you'd go 26.5 times 2 times 2 times 2 times 2 times 2. That gets you back to the original amount. For nuclear equations, you have to remember that the total mass and atomic number on both sides of the arrow has to be the same. So whatever you need to do in order to make that work, keeping in mind that when you change the number on the bottom, that atomic number, you have a new element. You look up the atomic number on the periodic table, and that's how you balance those equations. The type of decay is based on the type of particle that's either absorbed or emitted. So alpha particles means alpha decay, that's the 4-2 with the He or the little alpha A symbol. And then electron beta particles means beta decay. And then just make sure it's the same total on both sides of the arrow. That's it.